Now that we've looked at how to set up the electrons around the atom, we're now going to look at how this is going to relate to bonding. So I've taken chlorine that we looked at in that last slide and I brought it to this slide. And then I'm going to add one more element here, sodium. Sodium has an atomic number of 11. So if we were to draw sodium, here's its nucleus with the 11 protons and 11 neutrons. And then the electrons around this are going to be situated 2 in the first orbital, 8 in the next orbital. That gives us 10 electrons, which leaves us with one leftover electron. We're going to put that last electron here in the outer shell. So sodium, in order to be stable, to be in its happy state, that valence shell has one electron. It needs 7 more electrons in that outer shell. Or, notice that if it loses an electron, that outer shell will disappear, and in its second shell it has 8 electrons. So sodium, it's a lot easier to lose 1 electron than to gain 7. So sodium is willing to give up that outer electron so that it can have 8 electrons in its valence shell, in its outer shell. Chlorine, remember, it has 7 electrons in its outer shell. It wants an electron. It needs 1 more electron to fill that shell. So what can happen? Sodium can give away its electron to chlorine, and then in that case, what that's going to lead to is sodium losing an electron, chlorine gaining an electron. So now sodium has 8 electrons in its valence shell. Chlorine has 8 electrons in its valence shell, and they're both happy. Something else has happened here as well, though. Notice that sodium, here, if we count up the electrons now equal 10. Sodium has 11 protons with a positive charge. What this means is that sodium has now become an ion. It has a positive charge, Na positive. Chlorine also has a similar situation, but a little bit different. If we count up its electrons, we'll notice that there are now 18 electrons. This means that chlorine is now negatively charged. You know that negative and positive attract, and so now we've created a bond here. Sodium is positively charged, chlorine is negatively charged. They attract each other. This is called an ionic bond. The reason it's called an ionic bond is because you have 2 ions that are bonding together. So that's an ionic bond. The second type of bond is what's called a covalent bond. And I brought the oxygen that we looked at before to this page here. And let's look at how we can interact with other things. So we've already looked a little bit about hydrogen. Hydrogen has an atomic number of 1, atomic mass of 1. So let's look at what hydrogen might look like. This is the nucleus. And around that nucleus we have 1 electron. In the case of hydrogen, because it only has 1 electron shell, it just needs 1 more electron to fill that shell and it would be good. It'd be good to go. It could just lose that electron as well and become an H positive ion, and it could do ionic bonding with different things. It could ionically bond with chlorine and form HCl, hydrochloric acid, and that's a possibility. But here we want to look at what happens in covalent bonding, so we're going to assume that hydrogen wants to get an electron. So what could happen is hydrogen could come and associate with oxygen. So notice oxygen has 6 electrons in its valence shell. It needs 2 electrons. So we could have a hydrogen. I'm just going to draw this as an H here so we remember it's hydrogen. Hydrogen could come over and it could share its 1 electron with oxygen. At the same time, oxygen would share 1 of its electrons with hydrogen. Now hydrogen has 2 electrons. It's happy. Oxygen now has 7 electrons. So oxygen isn't quite good yet. It still wants 1 more electron. So what could happen is another hydrogen could come along and form another covalent bond and share its electron. Now now hydrogen has 2, this one has 2, oxygen has 8, everybody's happy. This is called a covalent bond. The reason it's a covalent bond is because we're sharing electrons. Nobody is giving or taking electrons. It's a sharing of those electrons. What this means as well, though, is that if hydrogen were to leave, oxygen would not have enough electrons. And so this bond, if you were to compare the strength of ionic bonds versus the strength of covalent bonds are stronger because they don't want to dissociate and leave. They don't want to break apart because then they wouldn't have enough electrons. Ionic bonding, NaCl, sodium and chloride, they can break apart and they'd still be happy. They still have enough. So another way to think about this is kind of like marriage, and ionic bonding is like dating. So in covalent bonding, these guys have a shared relationship. If anyone breaks that relationship apart, somebody's going to lose something. It's not going to work out so well. Sodium chloride, if they're just dating, they're attracted to each other, but they could break apart and they'd still be fine. They're not really losing anything. Maybe a weird example, I don't know, but maybe that's a good way to remember it. And I guess I should point out what we have here if you haven't realized already. We have 1 oxygen, we have 2 hydrogens, we have H2O, we've created water here. Water is a covalently bonded molecule. So now we've looked at the different types of bonds, and here they are again. So we have ionic bonds, which is when 2 atoms either gain or lose an electron, they become ions, and then they're attracted, positive and negative attracted together. Sodium chloride is the example we looked at. There are other examples. Covalent bonds are when you're sharing electrons. There's 2 types of covalent bonds. We have what are called polar bonds, and we have non-polar bonds. Notice that water that we just talked about is a polar covalent bond. If we go back to the water molecule here, this molecule is polar. The reason it's polar is because oxygen is a much bigger molecule, and so it has a stronger pull for the electrons. And what this leads to is it is an unequal sharing. Oxygen gets the electrons more of the time than hydrogen does. So what you end up with is a negative charge, just a slight negative charge on the oxygen side, and a slight positive side on the hydrogen side. Because if you have the electrons less of the time, you have less negative charge, slight positive, slight negative. So this is a polar bond. In the case of methane, methane is a non-polar bond. Methane is a relationship between carbon and 4 hydrogens. In this case, it's non-polar. Everything is sharing. The carbon is sharing its electrons equally with the hydrogen. It's a happy relationship here, so it's a non-polar bond. Okay, we also have something that is called a hydrogen bond. This is one of the major. There's a few different compounds that have hydrogen bonds. Water is the major one, and the reason that water has this type of bond is because of the polar nature of its bond. So we have one water molecule here. If we were to put another water molecule, and I'll just draw this one as an oxygen and 2 hydrogens. I need to put the hydrogen over on this other side. Let me try this one more time. Okay, so we've got an oxygen here, we've got a hydrogen here, a hydrogen here. Because oxygen has a slight negative charge, just like this water molecule here, hydrogens have a slight positive charge. These 2 molecules can attract each other. This is called a hydrogen bond. Weaker than an ionic bond, weaker than a covalent bond. It's just a slight attraction, but it leads to the properties of water, which we'll talk about a little bit later. And that's where we'll stop this section. So we've looked at molecules, we've looked at compounds, and we looked at bonding, and that is all determined by how the electrons are situated around an atom.